Hi everyone, welcome to this episode of Keipert Labs. In this Keipert Labs How-To video, we're going to go through how do we draw a scatter graph. Okay, so in a moment I'm going to show you up on the screen the exercise that this relates to. Okay, so what you can see there, you've got a table of data on the right hand side and then some instructions and some questions on the left hand side. The first instruction says, using the graph paper provided, which hopefully you will have in front of you now, create a scatter graph of the data in the table on the right. Make sure you include all relevant features of a graph. Okay, so first, before we're going to go through drawing this, let's think about what those features are. What does every good scientific graph need to have? It needs a title. Okay? Typically, the best sort of titles refer to the two variables that you're graphing. First variable, independent variable versus the dependent variable. Okay, we need to have a correct scale on both axes. Okay, and because we're talking about a number scale, scatter graph, we're talking about a number scale on both. Okay, so that is measurements going across the bottom for our independent variable and measurements up the side for our dependent variable. Okay, we need labeled axes. Okay, so that each of our scales has a meaning. We know what each number represents, and for things that are measured in particular units, that we identify what those are. That for a scatter graph, we're talking about plotting points on a graph. Okay, so we're going to say points plotted accurately. Okay, and we'll go through exactly how that works in a moment. And then we do a line of best through the points. Okay, so what you need to do when you're establishing a graph like this, go through this as a checklist. Have I got a title? Have I got a number scale on both axes that fits everything? Have I labelled my axes with their units, so a title and units? Have I plotted my points carefully and accurately? And then have I drawn a line of best fit through the points? Okay, so looking at this exercise, we're going to go through how this works now. Okay, so looking at the data in the table that you've got, okay, so I've got a sheet of graph paper here that I'm going to draw on. Okay, so we have two variables. Okay, we have drop height and rebound height. So I'm going to start with a title. I've got my piece going landscape, and I'll explain why in a moment. And I'm going to establish my title so that it's clear what my graph is about. So drop height versus rebound height for a bouncing ball. Okay, I appreciate it's a little off center, but we can live with that. Okay, so drop height versus rebound height for a bouncing ball. Okay, so I mentioned that we need to have a number scale across both axes. So we're going to establish that now. Okay, so I have a ruler here, so I'm going to use that in constructing my axes so that it's nice and neat with some nice straight lines. Okay, so the trick with a graph, or the thing that you need to remember, is that we always do our independent variable on the bottom, and then our dependent variable up the side. Okay, so I'm going to rule a nice neat line across the bottom, so make sure you do this as well when you are doing this exercise. Okay, and I'm going to do the same thing up the side. Okay, so my independent variable, the one that I am choosing to change, is the drop height in centimeters. So I've labelled my axis and I've given it, I've expressed the units that it's measured in. Up the side, I've got the rebound height, also measured in centimeters in this case. So now what I need to do is I need to establish a number scale that's going to fit the data that I need. So what I have to make sure is that my scale is going to fit the biggest number that I need to fit on each axis. So looking at my drop height, so it's expressed in meters actually, so I might change these from centimeters to meters. So I'm going to stick with exactly the data that you're presented with. Okay, so I've got to fit all the way up to 2 meters along this one. Now I need to make sure that each square counts for the same amount. Okay, so perhaps I might say that each big square counts for 0.1 meters. So every second one will be 0.2, 0.4, 0.6, 0.8, and then 1, 1.2, 1.4, 1.6, 1.8, and then 2. Okay, so that means that then my line is going to fit all of the values that I need. Okay, it needs to fit within the space. You can't extend it longer, but likewise you also don't want to cram it right into this area down the bottom here. So I'm only going to write these major points here. I'm not going to write every possible, like each point one, okay? Because I know what each one is going to be worth, okay? And then I'm also going to extend it out to here. Because one of the great things about a graph like this is that it allows you to look at relationships beyond your data. We can say what we extrapolate, or that is, or we can kind of work outside. Okay, so what we have here is I've got to fit up to 1.3. If I follow the same idea, so 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.3 would be here. So I've got a nice neat scale. I'm going to do the same idea, okay? Every second big square is going up by 0.2. So it's really important that when you're establishing this scale, that each marking is a consistent value. Okay, so that is that it's not like, okay, I've got 0.2 and then 0.4, 0.6, 0.8, and then 1, and like where it kind of varies. I also don't just write down the values up here, my rebound height of like 0.13, 0.25, whatever. Okay, that's how a line graph works, not a scatter graph. Scatter graph is a graph of measurements. Okay, so now comes the part about plotting the points, because I've got a title, tick. I've got scales on both my axes that are consistent and fit, tick. I've got labels and units on each of my axes. So now I get to the plotting the points and then the line of best fit. So what I do is that I look at I'm going to look at, and I'm going to put 0 in the corner, because that's what this point represents. So I'm going to read along until I get to a drop height of 0.2, which is my first number. And then I'm going to, along this line of 0.2, I'm going to read up until I get to the value that I need to plot. So my rebound height is 0.13. So I get to 0.2, and then I'm going to go up, and I'm going to go up to my best estimate for 0.13. Okay, now it's a bit hard with the scale, that I can actually use a ruler and I can be much more precise about exactly where I need to put my dot or my cross to get it right if I need to. Okay, so then 0.4, I'm going to do the same thing. I've got 0.2, and then halfway between 0.2 and 0.3, and then so on. I'm going to go up to 0.6, 0.4, and I'm putting a cross. Now you could put dots or you could put crosses. I like to try and put crosses because it helps me to say, well, the middle of the cross is that exact point that I need to plot. Okay, up here, and I'm going to 0.52. Okay, and then 1, 0.65, and then I'm going to keep plotting these points. Okay, so now I have my points plotted here. Alright, so now comes the last point that I've got to do a straight line of best fit between my data. Because the idea is that these are real-world measurements made in the lab, and so there's a certain amount of uncertainty in those measurements, or what we would call error, experimental error. And so what we want to do, though, is we can see that there's a clear relationship here, is that as we go along with our drop height, that our rebound height increases, and we want to come up with a general relationship that we can use for predictive power. So I want a straight line of best fit. So what that's going to do is a line of best fit will go as evenly as possible through the middle of the points that I've drawn. It's not joining dot to dot, it's using a ruler and doing a straight line that goes through these points. So I'm going to set it up. So it's going to look something like this when I do it. Okay? Now I'm going to make sure that my point lines up through 0, 0, because it makes sense that if I have a drop height of 0, I should also have a rebound height of 0. That in terms of a physical meaning, that makes some sense. Okay? And so then I'm going to, making sure that my line will line up with that, then it's going to fit as evenly as it can through each of the points that I've got. I'm going to use my ruler to draw a nice, neat, straight line. And I can extend that line beyond my data, okay, with some confidence, because I've developed a relationship so that we can then predict and say, well, actually, if I go to 2.2 meters, then I've got a good chance that it's going to be a rebound height of about 1.45. Or if I go to 2.4 meters, that it's going to be somewhere about 1.57 meters. Okay, I can use the line to make a prediction. I can also use it to predict within my data. So if I'm trying to ask, as one of the questions is, predicting the rebound height drop from 1.5 meters, I can read along until I get to 1.5. go up to the line and see, oh, my prediction is that it will be at 1 meter exactly. Okay, so that's how we draw a scatter graph. We set up a title, we do scale, we do axes on each scale, we put the independent down the bottom and the dependent variable up the side. So consistent number scales, titles and units on each axis. We plot our points accurately, going across and then up, a bit like coordinates in geography, and then we put a straight line, or we put a line of best fit. Now in all situations you're going to come through, it should be a straight line. Sometimes it could be a curved line if the relationship isn't a straight line. But all the sorts of ones we will deal with are, and so then we draw a nice straight line, and there's our scatter graph. Okay, thanks very much for watching. Bye for now.